Hi everyone, I'm going to show you how to take data recorded by our enDAQ devices and analyze that in Python to look at some time series data, but then also do some frequency analysis, and then specifically at the end show how you can correlate acceleration to the dominant frequency in the environment. So this is a tool called Colab. It's by Google. It's completely free. It's where you can do some Python analysis as well, taking detailed notes all here in a web browser like a Google Doc. So I'm importing some libraries here, including our open source IDE lib, and then I'm defining some functions that I'm going to use throughout this example. And now here I'm going to import the file. Now, some of those hidden functions that I just declared are going to be addressed in a open source library that we will release soon. So here I'm uploading a file that is a few megabytes, and this is from some vibration data on a motorcycle, and so it varies over frequency, which is what I'm specifically interested in. It takes a moment or two to upload it. If you have the data already web hosted, that's nice and easy. You can just pull it in from a URL. So here we load the data with some example functions. We see what's in this recording file. Our enDAQ devices, as you know, can record many, many channels, but in this example, they happen to just use the accelerometer X, Y, and Z. And so here I actually loaded all the data now, and I can see some metrics, standard deviation, the max min per channel, and I can plot these metrics over time here. So you see how the peak changes throughout the 90-second recording, the standard deviation changes in the X, Y, and Z axis. I could save this as an HTML file that would be over here. I can download that. And now if I open that, and I can send that to a colleague or whomever, or a customer, and this is now a completely interactive figure that you can access without having to log into anything. Okay, so now we want to get the acceleration data in a table format. So these are in data frames. Now I have X, Y, and Z as a function of time. And I can plot all the data with a built-in tool called matplotlib, which is built into Pandas. So it's just, once I have this data frame, I can do df.plot, which is nice and easy. The problem is this isn't very interactive, and that's not that fun. So I can use Plotly to plot an interactive version of this. Now, the one thing to be wary of is Plotly is going to be loading all the data with JavaScript in your web browsers, rendering it. So you want to be careful not to try to plot too much data. And that is the benefit of matplotlib, is you can just plot everything and it will intelligently figure out how to render it. So here I'm only going to plot the 5 seconds around this peak area, which is very easy to index, just doing 40:45. And here now I get the time series data in that period of time, and I can zoom around and you can turn off different axes, just look at the Y, which is what we're going to look at throughout most of this. And you can see there's clearly some intense vibration with a lot of different frequency content, but there's clearly one fairly dominant one, right? So now we can generate a power spectral density. Here's the helper function, and now here's the plot, and here's a power spectral density across the whole recording. And I specifically made a 1 hertz bin width, and I can, again, zoom around and do all that here in the browser. Now, I can, if I'd like to, change the frequency bin width, or I could change the time range in my power spectral density. And, if we look here at the raw data or in this this moving metrics, we notice that the vibration levels change over time. So maybe the frequency change over time. And so here I'll calculate a power spectral density for just that time range of 40 to 45 seconds. Clearly there's a peak around 100 hertz. But now if I do from 20 to 25 seconds, or let's just do 20 to 21 even, 2 seconds worth, there's a peak at 50 hertz. And there is also still one at 100, but it's not nearly as prevalent as the one at 50 anymore. So clearly our frequency range is changing throughout the recording. Now, we can do some other stuff like a cumulative RMS, which you can see how the RMS builds over the frequency range, and that's helpful to compare different recordings. You can generate an FFT, which I show in here. You can do a octave space power spectral density. But here, I'm going to now get to calculating a spectrogram. So here's a helper function, and now I'm going to render the spectrogram of the y-axis data, which you can see here, and clearly there's our frequency is changing throughout the recording. If I want to do, the x-axis, I've plotted that as well. So there we go. There's a lot more stuff going on the x-axis, but you can still clearly see that dominant frequency band. So now and you can do a 3D one as well. Sometimes the 3D ones look more cool than is practical to actually use, but there it is. Okay, so now we want to kind of do some analysis to see, well, let me get that peak frequency as a function of time. So here's a helper function to do that, and now here's the plot. And so this is a peak frequency as a function of time. We can, of course, calculate acceleration levels as a function of time and then correlate acceleration levels to the peak frequency. So here now, I've done that, and I'm going to actually convert the frequency to RPM, and I'm going to convert the acceleration levels from G to meters per second squared. And I'll plot the max, the peak, as well as the RMS levels. And then there you go. And that is a quick example on how to access some data from our devices, do some simple analysis, and end with comparing acceleration levels as a function of RPM. Thanks.